Welcome back. I hope you enjoy those shorts. If you haven't been subscribed on YouTube, I've been posting them as YouTube shorts over time. I have plenty more plans, and we have about a dozen or so out there with different explainers. So if you haven't seen them if this is your first time seeing them, please go over to containersfromthecouch.com and subscribe to the channel, because I have a lot of ideas and a lot of requests for new shorts. But I want to welcome Sheetal and Jeremy. Thanks for coming. And this segment, we're talking all about IPv6 with Kubernetes. And if you run out of IPs or you just want to see hex IP addresses, we got some hex IPs for you today. And we actually just did a show on this. Sheetal, we just had, who was it from the team?
We had Mike, who is a PM for EKS organization, and we had STE, who worked on the IPv6 implementation as well on the call.
Right.
Yeah. It was a great show. We had a lot of attendees that day.
Yeah, that was an awesome show. And that was 2 or 3 weeks ago. So if you want to see like a full, let's talk about everything IPv6 in Kubernetes, go check out the show in the channel. Today, we want to show you a smaller, 30-minute demo of what it looks like to run IPv6 inside of your clusters with specifically pod networking. So Sheetal, go ahead and give us an intro. You've been on the show before, but just for anyone else that's watching that has never met you.
Hi, I am Sheetal Joshi. I'm a developer advocate within EKS organization, and I'm glad to be here. And I guess we have done IPv6 I think many times, and the one recent was 2 weeks ago. Yeah, but I'm happy to deep dive IPv6 again one more time.
Love having you on the show. Jeremy, say hello. What do you do?
Yeah, hi folks. My name's Jeremy Cowan. I am also part of the developer advocate team at AWS. And I work primarily behind the scenes. I've been on the show a few times, but I'm glad I had the opportunity to come on today. Thanks.
Awesome. And I know, Sheetal, you have a demo for us, and I think you have some slides too, right?
Yeah, I'll be switching between slide and the demo so that we get a context. So the slide is not going to be in a slideshow mode, but yeah, not many slides. I'm not.
All right, no problem. Let me pull it in screen so we can go over it, because with IPv6, it's always nice to have some sort of diagram or visualization.
I know, yeah. And we have too many arrows connections, so I just wanted to bring up some slides so that we have a context. Why IPv6 and EKS, right? Before we get into an IPv6, I just want to talk about a brief history about what CNI is and what VPC CNI and how it works today. CNI is nothing but, the network specification. It is a set of standards, and the specification and also comes with a set of libraries, right? So what does CNI do for us? In the entirety of the Kubernetes networking, the cluster networking, and also called as a pod networking, is an important bit, right? And CNI actually helps us assign basically an IP addresses to a pod. It creates a network namespace, and it actually creates that network interface into the pod as well. And as the pods go through their life cycle, it helps clean up that network namespace and also clean up the IP that is assigned to the pod. There are different implementation types when it comes to CNI. I guess we have actually heard about an overlay CNI, routing, or an underlay. So overlay is typically when basically connections are established through the tunnels between the nodes, and the packets are encapsulated so that an underlay network doesn't get a handle of it. And a routing is usually when we establish a routing, and also it depends on an underlying network, and then there is no tunnel, right? An underlay is where the connections between the containers and hence the pods uses the underlying network capabilities. And in AWS terms, that underlying capability is already provided through a VPC. And the CNI that actually we leverage today within EKS by default is a VPC CNI, which runs on an underlay network. So what is a VPC CNI, right? It's a native VPC networking CNI plugin, which works on top of the VPC. Pods, because it's an underlay CNI, pods get the same VPC IP and as well as the nodes. And it's very simple and secure networking because it actually leverages all of the VPC features. And another cool thing is it's an open source you can actually look at the code and also provide the fixes and create the issues and be part of one of the community member, right? And that's a great way to contribute as well.
Hey, Sheetal, I have a quick question.
Sure.
So you talked about underlay and overlay networks. Is there an advantage to using an underlay network?
Yeah, so because there is no tunneling and the encapsulation, it becomes usually faster, right? And also you can enable the flow logs and then see what is happening on the wire using the VPC features. That's one of the coolest features. And you can also get the benefits of the encryption that VPC brings in as well. Yeah.
Nice.
Okay, so how does a VPC CNI work, right? Because each of the pod gets a VPC IP here. So whenever the pods are scheduled, so when the node actually is spin up, a worker node is spin up, so we have a primary ENI that is, actually assigned to the node. And when the pods are scheduled, actually the pods get an IP address, and those pods IP address are a VPC IP that are assigned as a secondary IPs here. And we have, as and when, for each of the instance type, there are set number of secondary IPs. And each of the instance type have the limits. And as we see the secondary IP limits is exceeding, we assign one more ENI, and that goes up till we reach the limit of an ENI on an instance. So you can now think of, okay, then if I want to run more pods, or if I am running into an IPv4 exhaustion limits, what it is, right? What it is for me. So I think for the pod density issue on a node, we kind of introduced something called as a prefix delegation. We launched a feature, like EC2 launched a prefix delegation feature, and the CNI makes use that feature. And in that, and we do assign a prefix instead of direct secondary IP, so that you can actually limit the number of the pods that are running on a node. So kind of working backwards, right? Kubernetes actually support dual stack, which is IPv4 and IPv6 from 121. But for us, because our customers have experienced the IPv4 exhaustion limits, and actually going with the dual stack is not the way to go. And our primary use case was to solve an IPv4 exhaustion for our customer. And we also live in this real world where actually some of the applications are still IPv4, IPv6 is the North Star, but we do have many of the services and also our customers still running an IPv4. And also some of the AWS services as well support IPv4 today, right? So we wanted to solve IPv4 exhaustion problem and also enable customers to talk to these traditional IPv4 services, and whether it be on-prem or on our AWS services. Plus, we wanted to maintain a high-performance networking for our EKS customers and provide a seamless migration path. So how did we actually solve this? Definitely, it's not upstream IPv4 and IPv6 dual stack. So what we thought was maybe we will just go with the pod IPv6 network, and that's what this feature is about. Before
real question, since you just were mentioning it, question from the chats. Why does dual stack not solve IPv4 exhaustion?
Yeah, because in the dual stack, pods and the services still receive an IPv4 address, right? And if we had implemented the dual stack, pods would have still be requiring to get an IP from our VPC range, and we would still hit the IPv4 exhaustion problems. So, and that's one of the reasons that we didn't want to go with an IPv4 and IPv6, which is a dual stack. However, we do support IPv4 egress and IPv4 ingress with this IPv6 only pod networking feature. Before I get into how we actually implement IPv6 on EKS, just a little bit IPv6 fundamentals here, right? As we know, IPv6 is a larger space, which is 128 bits versus 32 bits of IPv4. And if you think of, we have enough IPv6 address to assign each IP to like every grain of sand on the earth, right? So that's how large it is. It's globally unique and hierarchical addressing. We do have different IP addressing schemes within IPv6, like which we call as global unicast address, which is 2000 range. And there is also something called as a unique local address. And this is, you can think of it as a private address spacing 1918, RFC 1918. And linked local unicast address is, if you have to relate it to an IPv4, we have something called as a host local non-routing address, which these addresses are only available at a node level and not beyond routing point. And those are usually FE80/10, and then the multicast. So how do I?
And that's important to call out the no local, because the pod is getting an IPv4 address. It's just not coming from the VPC. We say, hey, the pod gets it from a node, and that's how we can still route to IPv4 addresses, but you're not using an IPv4 space from the VPC and running into those exhaustion problems.
Yeah, this link local is still IPv6. So every pod will also get a address from the global unicast address as well as a link local address. And we will talk about the IPv4 egress solutions that we have implemented in a little bit, actually, Justin. So this is just the IPv6 link local that I'm talking about right now. Yeah. And the IPv6 addresses can be assigned statically or through the DHCP-v6, and also something called a SLAC, which is stateless address auto configuration. And with IPv6, we can actually leverage all the built-in authentication and the encryption as well. So one of the biggest tenets for VPC CNI is we would want to iteratively improve the experience along as VPC launches the new features, or the EC2 networking launches the new features. So VPC, we launched actually a dual stack mode. VPC can operate in a dual stack mode, which means resources can communicate over IPv4 as well as IPv6, right? And IPv6 and IPv4 addresses are independent of each other. Routing and securities are, as you see in the route table here, the routing and the securities are independently configured for both IPv4 and IPv6. And one of the biggest mind shift with IPv6 is there are no private addresses, right? Everything becomes public. So how do we actually implement public versus private subnets that we have been used to? And the way that we do is, for the private IPv4, there is something called as egress-only internet gateway, which allows all of the egress communications versus stopping any incoming connections from the internet. So that is egress-only internet gateway. And I just briefly talked about the prefix delegation. Within IPv6 world, we have /80 prefixes that can be assigned to the node. So the VPCs get /56 IPv6 addresses from the global unicast range that have been assigned to AWS. And each of the subnets are /64, and the prefixes that node we can assign to the ENIs at the node level are /80. So let me go through the VPC basics that I just covered. I'm just bringing up one of the sample VPCs that I have used to spin up the cluster. So what we see here is it has both IPv4 CIDR and as well as IPv6 CIDR that is associated. That if you see here the /56 and from the 2600 range. So let's go to one of the subnets basically. Let's see how the private and the public subnets have been created here. Yeah. So the CIDR range that we do see for the subnet is /64, and the route table, this is one of the public subnet that I'm sharing. So it goes through the internet gateway, and the private subnet, if you see the route table entries, it will be egress only internet gateway, right? So let's jump back to our presentation. So how does EKS make use of all the cool benefits that VPC and the EC2 networking provide? So support for IPv6 within EKS is, we definitely wanted to scale beyond IPv4 limits and simplify pod networking without any network address translation. Because of IPv4, there are so many overlapping CIDRs problems that we get into, and then there is a lot of network address translations that we actually have to deal with. But with IPv6, all of those complexities will be gone. And we just talked about how VPC CNI actually works, right? We create ENIs, and then we assign the secondary IPs in an IPv4, and that means we will have to keeping the worm pools, and also as we have the highest pod churns in large clusters, we do see not a delay per se, but there is a time that is actually taken to get those IPs. But here in an IPv6 world, because there is only one prefix that is required, and that is assigned to a node at the node launch time, we don't have to make those frequent calls, which actually results in a faster pod launch times as well. And with the egress IPv4 solution that we'll just talk about, gives us a benefit of both connecting to IPv4 as well as an IPv6 endpoint as well, right? So it's technically, at the end of the day, it's a single stack Kubernetes with a dual stack pods. That's how you can remember it. Amazon EKS cluster, basically it's a 3-layered, right? So we have the Amazon managed EKS control plane. And then there is the Kubernetes control plane, which is managed by Amazon, and which is actually a single tenant EKS control plane and runs in its own managed VPC. And then there is the data plane, which is all of your nodes in the pod, which run in the VPCs that is managed by you, right? And IPv6 actually, the support for the IPv6 is at the customer managed VPC and the data plane, trying to solve the pod IPv4 exhaustion problem. So as of today, the Amazon EKS control plane itself and all of the AWS APIs are in IPv4, although we are actually working fast to support the IPv6 at the API layer, wherein the Kubernetes control plane itself, the API server, is IPv4 as of today. Kubernetes API server is front-end by a network load balancer, and the network load balancer in an instance target mode basically loses the source IP address, and that we require for the audit logs, and that is the reason it's only IPv4 as of today. But everything below here inside of the customer managed VPC is all IPv6. Even your services actually get an IPv6. So let's go to look at the cluster that I have provisioned already.
Sheetal, I have a quick question. So
Sure.
Let's say I'm a customer and I'm experiencing this IP exhaustion issue that you were describing earlier. Is there a way for me to enable IPv6 in an existing cluster?
Right now, it's not a possibility. So you will have to create a new cluster and then enable the IPv6 and do the migrations. You cannot basically, just enable IPv6 and then your cluster will be IPv6. That's not how it works today.
Okay. Okay. Oh, and I also see a question in the chat here, and you may talk about this here momentarily, but FOE6, hopefully I'm pronouncing that correct, says, what is the difference between the Internet Gateway and the egress Internet Gateway?
Yeah, egress Internet Gateway allows you to basically, it just allows anything going to the internet, but it stops all the incoming traffic so that your private IPv6 subnets kind of behave the private way, because in an IPv6 world, there is nothing like a private, addresses, right? Everything is public, but egress Internet Gateway, yeah, provides those benefits for you.
Okay, great. Thanks for the explanation.
So for the purpose of this demo today, I have already created or provisioned an IPv6 cluster. So what we see here, you will just provision on the cluster as usual. As of today, there are not major changes. The experience remains the same, except that you're going to go ahead and say my cluster IP address family has to be IPv6. The default is still IPv4, but if you want an IPv6 cluster, you will have to specifically specify an IPv6 cluster IP family, right? And what you see is a service IPv6 range. This service, you cannot customize the service CIDRs today. It is, we do assign automatically the CIDR from the unique local address range, which is from FD/8. And that's what you're seeing here, one of the CIDRs that we automatically assigned to this cluster service IPv6 range. We still support all of the three modes for our API server endpoint and also the cluster type configuration, which is public, and private. Just for the demonstration purposes, I have provisioned the cluster in public and the private mode here. So how does the cluster communication work, right? Because we did say that Kubernetes control plane runs in a managed VPC versus all of your workloads and hence the nodes, the entire data plane is in your own VPC. We do provision something called as a managed ENI, which are also called as XENIs or XENIs. And these XENIs in an IPv6 cluster are provisioned both IPv4 as well as IPv6, or we do assign IPv4 as well as an IPv6 endpoint. Any communications from API server to the nodes and to the pods is always through the IPv6 link. However, because API server is only in an IPv4 mode, any communications from the node components such as kubelet, kubeproxy, all those go through the IPv4, and as well as pod communication to our API server goes through an IPv4 model. What you see here is an ingress into the cluster. We do support the controller elastic load balancer, and that supports both IPv4 as well as IPv6. So what does that mean is, if you want to expose your applications or workloads outside of the cluster, you can still leverage the ELB controller and specify an annotation saying that I want to expose it is in a dual stack mode. You will get both IPv4 and an IPv6. Your services and hence any of the load balancers that are provisioned, or if you are provisioning an ingress, the application load balancer, do get both A as well as CORD ADNS records, which would resolve to IPv6 addresses directly. Okay, let's jump ahead, and then what I'm going to do here is I'm going to deploy a sample application. As you see here, there are no specific annotations, right? You just deploy a pod normally as you're deploying any other pod. I'm going to go ahead and apply the sample app, and let's visualize the IP assignment. Okay, so I'm just exiting into this pod. So what you see here is two interfaces, right? Why two interfaces? First one is the IPv6, and then second one, there is an IPv4 address along with the link local address that IPv6 assigns. So why are we doing this, and how did we do this, right? Although we want everybody to use and migrate to IPv6, we still have to realize most of our customers as well as our services and applications are still IPv4. We wanted to provide a flexibility or also an option for our pods to be able to connect and resolve to an IPv4 endpoint. And that's the reason we have implemented something called as a host local CNI, which runs in a CNI chaining mode. So let's see the nodes that I have provisioned here. So I'm going to log into one of our instance. Yeah. Let's go to the instance. Yeah, I'm using a session manager to connect to one of the nodes within the cluster. So what you see here is CNI plugin configuration, and the main plugin is all IPv6, and we have a egress v4 CNI plugin that is changed. And Justin, this is going back to what you were bringing up earlier, the egress only IPv4 solution. And for that, we configure a host local IPAM type and use a subnet range 169.254, which is from the host local non-routing CIDR range, and /22. And /22 is almost around 1,000 IPs. And you might ask, why only 1,000, wherein you're configuring a /80 IPv6 CIDR versus 1,000 range CIDR for an IPv4. But typically, you would exhaust the node resources before you exhaust the IPv4 IPs here. And let's go back and look at basically the IPs that have been assigned here, and also examine the pod. When I actually describe a pod or get a, let me describe a pod. The IPs that you see here on a pod are only the IPv6 addresses, and you would never see an IPv4 address that has been assigned to a pod, which means the Kubernetes API server and the control plane will never see that host local IPv4 address that has been assigned to a pod. So how does it all work, right? So let's look at the pictorial representation, basically. Yeah, this is just a recap. So the IPv6 networking, the CNI, when you provision the nodes at the boot time, a single prefix is assigned to the node, and all the pods receive an IPv6 address from that /80 prefix, right? Any pod-to-pod communication is always via IPv6. Pod-to-pod will not see the IPv4. Any IPv4 initiation at the pod level will be blocked. And pod to external IPv6, if you are running within a private subnet, and that as per the best practice, you would want to do that. And it goes, your connection will reach the ENI, the primary ENI, and it goes through the egress only internet gateway. And any ingress into your workloads or an application is always via, you would want to use the load balancer in a dual stack mode to enable both the IPs. Pod to external IPv4, that's where our host local CNI, the chaining that we talked about, comes into play. Pods get IPv4 as well, along with the VPC IPv6 CIDR. And any connection that is to an external IPv4 endpoint will be NATed to the private IPv4 address that a node receives. And then depending on how you are running your workloads and the subnets, it goes through the NAT gateway and via the internet gateway to the outside IPv4 endpoint. VPC recently launched something called as NAT64 and DNS64. We have to implement and use the features like maybe shortly, yeah, I cannot comment on the exact timeline, but we are working on to integrate the NAT64 and the DNS64. Maybe when we integrate that, probably the egress only IPv4 solutions that we have in place might not be required, but that's coming soon.
Sheetal, we're right at time for Michael. So I'm going to pop out your screen. I did put in the comments the full talk we just did 2 weeks ago. So if I know you still had more content, like I want to get to it, but we also have another show after us. So I'm trying to keep this on time.
I just wanted to show how you can actually provision the dual stack.
Right, with the annotation.
Yeah, annotation. Yeah. So you can expose your applications using either ingress or the service type load balancer, and the load balancer support the new annotation type, which is called as a dual stack. And when you do that, you will see both the DNSA and quad A records.
Right. And that's a dual stack on the load balancer, not the pod. So the load balancer knows, hey, I'm looking at both IP addresses, route to me via IPv6 or IPv4, and the load balancer gets that. So yeah. Awesome.
Sure.
So I'm gonna pop that out just so that we can keep moving. But I mean, we already had some great comments and people looking into it. Like this is the next wave for a lot of people on reaching higher scales in Kubernetes. So we want to make sure that we're giving you the information and sort of enabling what you can do in the future with this. But for now, yeah, you do have to create a new cluster. VPC needs to have IPv6 enabled. So yeah, I'm excited for it. I've tried it a couple times, and I think we're only gonna make this easier over time. IPv6 support is gonna come even more native to the VPC and to Kubernetes and to pods, and hopefully people don't have to worry about the networking. Like it is a fascinating topic with lots of like performance benefits, but also like it's a lot of information to for like an application developer to be like, what am I doing here? And you actually mentioned, Sheetal, that like there was a, oh, I added it. Where'd it go? I added another. I love what you said. You're just like, but how does it all work? And I'm like, that's a new banner for the show, because it's like, that's just like what we try to get to in all these cases, is just like, how does it work? And you did a fantastic job explaining that in the pod itself. So anyway, I'm going to jump to another quick video, and then we're going to bring Michael on to talk all about Grafana and observability. So we'll jump to one more video, and Sheetal and Jeremy are staying with us. So we're just going to add one more to the couch, and we will be right